Good morning, FOR 345. Welcome to another exciting lecture. I'm here in the ESF TV studio. I'm actually at the Soil Science Society of America meeting, and hence you're getting me live, but live now, and you're getting me recorded. So today's topic is we're going to finish up water, and we're going to begin aeration. And here we go, because water, the test will be on all the water stuff. Aeration will not be covered. So some announcements. Remember, there's no lab this week. Exam 2, of course, is in 2 days. It'll be on soil physical properties and soil water. It will include some of today's lecture. So when we get to the end of soil water, I'll tell you we're there. And then you can worry about the details of the material for aeration and temperature and so forth in the next exam. So last time, where are we at? We are getting toward the end of soil moisture. We have some to wrap up today. We talked about the factors affecting available water. We talked about thickness, soil structure, compaction, and layering, and that's where we're at. And we talked about water flow, its response to gradients, and we went through all the different gradients from free energy up to thin and thick films. And we talked about saturated flow. We illustrated Darcy's law and kind of identified the little piece of that saturated hydraulic conductivity, or KSAT, and we related that to soil texture and structure. And we stopped there, and unfortunately we had to stop because we ran out of time, but now we have to cover the other piece of flow, and that's unsaturated flow. And this is driven by matrix potential. And after all the gravitational water leaves, the soil is at field capacity, and now we're dealing with unsaturated flow. Water still moves, but at a much slower amount and quite a bit of a slower rate, as we'll see. So what drives unsaturated flow? Saturated flow is driven by a gradient in gravitational potential. The gradient that drives unsaturated flow is matrix potential, and we've talked about that. We've represented it, psi sub m, total soil water potential, the portion due to the matrix forces, the attraction of soil solids for water. And the rates, this is a much slower, smaller amount of material moving. It's about 1,000th and smaller the rate of saturated flow. So this is an order of magnitude difference in terms of flow rates of 3. So that's substantial. It doesn't make it unimportant, it just makes it a little bit different scale. Now, in general, the rates of unsaturated flow, hydraulic conductivity unsaturated, K unsat, higher for finer texture. The more clays, the greater the potential rate in unsaturated flow. So finer textures, greater rate of unsaturated flow. And you can see why. It's driven by matrix potential. So let's look at this in a diagram from figure 523 in the text, right? And so it shows saturated flow, and there we're at saturation. We have potential, water potential is 0 by definition, so psi, the soil water potential, is 0. All the macropores are filled. Okay? The macropores begin to empty. Okay? So water flows out, gravitational water leaves. And then we get to a situation, we are much drier, and we get to field capacity, and we start going below that, and now unsaturated flow occurs. Unsaturated flow, water still moves around, but we're not moving through macropores, we're now moving through micropores. Okay? And again, this rate of this is 10 to the 3 orders of magnitude difference. So let's look at that in a graph. So this graph says a lot. Now you should know this graph and use it because I'm going to ask you about these concepts in the test. Right? And so this graph plots hydraulic conductivity, centimeters per day, log scale. Okay, we've looked at the metrics for conductivity. It's amount of water per unit time, and here it's centimeters per day. It's a log scale. And we're plotting that versus matrix potential, soil moisture potential, largely due to the soil matrix. Again, log scale. So here we are at saturation. We go past and we get to minus 0.01 bars, minus 0.1, so forth. And here we are at the conversion to kilopascals, 100 difference. So we've talked about these scales. You should be familiar with both of these. Okay? And look at this graph. Okay? We have a sandy loam. It starts out with a higher rate of hydraulic conductivity. And then we have a clay. At some point, the rates switch. The clay hydraulic conductivity becomes greater and the sandy loam lower. So this is a switch. So it starts out this position, higher rate of hydraulic conductivity for a coarse textured soil. We get to this position here and we have a higher rate of conductivity for a clay soil. So this is pretty illustrative of the difference between saturated and unsaturated flow. So let me illustrate. What at this point they cross, these two curves cross. And what's the significance of this point? Okay? At around minus 10 to minus 30 kilopascals. This is field capacity. Right? And so this is the difference between saturated flow, where we're dealing with driven by gradient and gravitational potential, and this is the difference here. And when it switches over, this is driven by matrix forces, matrix gradient. Okay? And it switches over at field capacity. So when things are saturated, the water flow through the large pores is much greater for a coarse textured soil. A lot more macropores, a higher proportion of macropores. When you get to field capacity, it switches. Right? At field capacity, now all the macropores have emptied, the micropores are filled, and all the water flow is going to micropores. This is driven by the gradient and matrix potential. So for a clay, the rate of hydraulic conductivity is much greater than the rate of hydraulic conductivity for a coarse textured soil. So essentially we're looking at saturated flow here, unsaturated flow here, and they cross at field capacity. So all those things connect right now. So that brings me to a question. How do nutrients and pesticides move through the soil rapidly? Saturated or unsaturated flow? Which one? And again, we're picking up where we left off from last lecture, last week. Okay? They move rapidly through saturated flow, right? And we showed this diagram, this picture, and this is the illustration of movement of water, saturated flow, preferential flow through large channels, and a lot of water moves this way. And we talked about contaminated plumes and how they arise. Okay? Preferential flow. Again, reinforcing what we talked about last week. And the next piece I want to talk about is the vadose. So we also mentioned that hydrogeologists are interested in the groundwater table. As soil scientists, we kind of focus on the unsaturated zone, the vadose zone. And so when we look at our total soil water potential, we don't usually think much about hydrostatic pressure. If you're in geology or hydrogeology, you'll be thinking about hydrostatic pressure. Okay? So we think about the vadose zone, but not that vader. Okay? The vadose zone, the definition. The vadose zone is the aerated region of soil above the permanent water table. Okay? So that's a new definition for us, the vadose zone. I think I've mentioned it before, but now we'll add some words to it and add it to our vocabulary. The aerated region of soil above the permanent water table. So let's have a picture of that. All right? So here is an illustration of tree roots and so forth. We have a zone of unsaturated. We have tree roots, and then below that, and all of a sudden we get to this capillary fringe. We defined the capillary fringe earlier as the zone of moist soil above the water table due to capillary rise, and then the saturated zone. Okay? So here we are at the groundwater, and this is the difference. And so we usually focus, again, on the unsaturated zone. Okay? And so this is the vadose zone. It includes the capillary fringe. Right? This is some water wicked up, but not all the pores filled with water. So generally, everything above the water table is the vadose zone, the unsaturated zone above the water table. Pretty cool, right? Vadose zone, unsaturated. Again, we're soil scientists. So let's look at this idea of a forest soil and think about these large pores and go back to how so much water moves through. This is a cross-section. This was some work done by the Forest Service in the 60s and 70s, and they examined, the question was, why is it in forest soils do we rarely see overland flow? Forest soils are natural, we use for our natural rates of erosion, natural erosion. This water flows through the system and not over it. And the reason largely is two things. One is the forest floor. So the forest floor absorbs the impact of drops coming down and distributes the energy. The next part of that, water moves through preferentially and is stored in large channels. But in forests, we have a lot of old decay root systems, we have old root channels, we have animal burrows, and so we actually have a system of megapores, large biotic pores, on top of what you normally have in other systems. And these are able to store and move a tremendous amount of water. So you can throw a hurricane force storm at a forest system, and that water will not overland flow over the water, flow over the land. It'll flow through the system and be absorbed, and hence no erosion. The combination of the forest floor and the canopy and these megapores eliminate erosion. So forest systems are natural rates of erosion. They also estimated the areas of those. So these scientists, this was actually in Ohio, it was in an oak stand. And so scientists took this apart. They started out, they had like a 8-foot long trench around this very large area, put water at the top, and then measured the outflow and saw no overland flow. Then they took this apart. They took apart this in pieces and blocks and plotted it. And so that plot you see is a cross section of what that looks like down to the 4 feet depth. And in doing that, they estimated the percent of biotic macropores. So if you look here at the A horizon and the E horizon, large proportion of that surface consists of large biotic macropores. And so that's pretty impressive. And they decrease with depth. And so think about saturated flow through forest soils with that picture in your mind, right? A lot of that flow is through macropores, and specifically the large macropores, megapores, root channels, animal and insect burrows, very large spaces to allow for essentially whatever nature can throw at it. And most of those channels are found in the upper solum, right? The upper 2.5 feet. In finer textured soils, they persist for longer times, which is kind of counterintuitive in finer textured soils because the increased structure and the ability of these particles to hold together, these megapores persist particularly in root channels in fine textured soils. So where does water move through? Water, free water, moves through the megapores. And we said before, this is at least 100 times matrix flow rate. So most of the water is moving that way. Much of the fine textured soil can be unwetted. Okay, so we looked at saturated flow through forest soils. This pretty much ends our discussion of soil water. And now it ends this topic. So everything up to this point, through this point, will be covered on the exam, all of soil water. We're going to move to soil aeration, and that will not be covered. That'll be on the next exam. So you can draw your line there and leave your intensive studying for the soil water piece. And again, hopefully you attended the session on Friday, the review session. We have the text, and very important, look at your lab notes, study your lab reports, because some of those questions from the lab reports you'll see again on the test in one form or another. And remember, the lab is integrated with the class, and they both are required, and so they're both fair game for exams. So we go to soil aeration. And probably a good place to start is thinking about the concentration of the gases in the soil as well as in the atmosphere. And so if we look at this graph, this shows the concentration of the three big gases, nitrogen, oxygen, and CO2, and their partial pressures in the atmosphere. Nitrogen 78%, oxygen 21%, and CO2 about 416 parts per million, or 0.0416%. It's actually, this is 2022 data, it's actually 418. Okay, so these are relatively decreasing concentrations as we go from nitrogen to oxygen. Nitrogen is pretty stable. Oxygen will change as it hits the soil, and so will carbon dioxide. So then we compare that to the soil air. The concentration of nitrogen in the soil air is about the same, the biggest percent. It's inert. And if we look at what is the concentration of oxygen in the soil air, it's lower than the atmosphere. And lower, how much lower, depends on a bunch of variables that we'll talk about. Okay? The same is true with carbon dioxide. The concentration of carbon dioxide in the soil is higher than in the atmosphere. And how much higher depends on several of the variables we'll talk about. So this leads us into that discussion for soil aeration. Other gases, methane, hydrogen sulfide, C2. So there's a whole bunch of other gases, but these are in micro quantities. So the big three that we'll talk about for the most part, nitrogen, oxygen, and carbon dioxide. We will mention some of the other ones. So what is a well-aerated soil? We need a definition to understand. We talk about aeration, so let's define that. Right? A well-aerated soil is defined in terms of gas exchange. So the beginning of this definition starts with a few words, a gas exchange sufficiently rapid to do something. Okay? So well-aerated soil, we're referring to a gas exchange rate sufficiently rapid to meet certain conditions. So what are those conditions? Well, sufficiently rapid to replenish oxygen, O2. Oxygen is needed by aerobic organisms. It starts to get in short supply and productivity goes down. And so we need to keep it coming into the system. And so replenishment, well aerated, means that we are replenishing oxygen sufficiently. Building up at the same time because of respiration is carbon dioxide, CO2, and needs to be removed. And so well-aerated soil has both of those things going on. We're replenishing oxygen, O2, gaseous oxygen, and we're reducing or preventing the buildup of carbon dioxide, which gets toxic at a certain point. So this is a well-aerated soil. We need to keep those things moving. Oxygen coming in, CO2 going out. What determines that? What determines the oxygen availability in the field, in the soil? Well, there are several things regulating it. The first thing we think about, and we're now building on our soil texture and structure, our soil physical properties lab, so this is why we save aeration until after water, soil macroporosity, and that's driven by texture and structure. Right? So water flows freely through macropores. When the macropore is empty, air is able to move through. And so you can replenish the oxygen, you can get rid of the CO2. This depends on macropores, soil macroporosity. And again, that's driven by texture and structure. The second part of that is the water content air-filled porosity. How much water versus how much air. Those two things shift. In a pore, either water or air. The third thing is consumption. Oxygen is being consumed, and at the same time, respiration is taking place, and CO2 is being produced. So the rate of consumption and the rate of CO2 production from respiration, and roots are respiring, soil organisms are respiring, this is part of the factor that drives the availability of oxygen, how fast you use it. So how much there is, how it moves around, how fast it's used. So what about gas exchange? What are the mechanisms? Well, gas moves two different ways. Moves by mass flow. Those are big differences in pressure from atmospheric pressure. And it also moves by diffusion. Now the mechanism we'll focus on, the major mechanism here in capital letters that does all this exchange is called diffusion. The movement of a gas or a substance against a gradient. So diffusion is the driver. This is the mechanism. So let's illustrate that. In the text, there's a picture on page 286, figure 7.3, that shows this cartoon of the atmosphere and the soils. Okay, here's the soil line. This is the soil surface. And in the atmosphere, the concentration of CO2 relative to O2, small CO2, a lot of O2. So, and in the soil, okay, the concentrations are lower. We said the concentrations of oxygen in the soil were lower. The concentrations of CO2 in the soil were lower. But now, how do these gases move from one place to the other? And it's by diffusion. Okay, diffusion is the flow in response to a gradient. Okay. So in the soil, the concentration of CO2 is higher than the atmosphere, right? So represented by these yellowish dots. Okay? So the concentration, the gradient, is high concentration to low concentration. So CO2 tends to diffuse or move from the soil to the atmosphere by diffusion. There's a higher concentration in the soil, there's a lower concentration in the atmosphere, and so the movement is to the atmosphere. With oxygen, the concentration of oxygen atoms is higher in the atmosphere than the soil. So here the gradient, the diffusion gradient, is from the atmosphere to the soil, and again, by diffusion. These movements in response to a gradient. And the gradient is the partial pressure of the concentration. And if we look at where does this take place? This takes place in air-filled pores. If they're filled with water, it slows down. In fact, it's negligible. So we here note this little note here on the top of the slide. Diffusion is about 10,000 times greater in air-filled pore space compared to water-filled pores. So essentially, diffusion, this mechanism, is taking place in air-filled pore space. Got to have the air-filled pore space, and this is macroporosity. Right? The large pores empty, and then they're available to move move gas through. How do we assess soil aeration? We've defined it. We've shown the major mechanism. There's diffusion. There's a little bit of mass flow, but diffusion is largely the major. And so how do we assess it? And so that's the subject of this. We have a variety of ways to quantify it and describe it with metrics. Okay? One way is the content of oxygen and other gases. So you should know these cutoffs. Oxygen, the partial pressure, 10%, 0.1 liter of oxygen per liter of volume. Most upland plants require at least 10% of the atmosphere to be filled with oxygen. Okay, so the roots need that. So if you keep your partial pressure of oxygen at 10% in the soil, you're good. When you start to drop below that, it's not good for the plants, and we start to run into trouble. So this 10% oxygen is a cutoff for good aeration. More than 10%, okay. Less than 10%, impeded. The same is true, but in reverse, for carbon dioxide. So carbon dioxide, 0.1 liters per liter, 10%. When that exceeds 10%, that becomes toxic to most upland plants. So the root systems have a tough time. You start to get oxygen and also the bacteria and fungi. When you elevate the CO2 above 10% concentration, then you're in difficult spaces. Right? It's toxic. And so you've got to keep that below 10%. Or keep the oxygen above 10%. So these are measures of aeration. A well-aerated soil will have an oxygen content greater than 10% of the airspace. A poor aerated soil will have a carbon dioxide concentration greater than 10%. Okay, the second way we can think about this, besides concentration, air-filled porosity. Okay? And so air-filled porosity we express as a percent of total pore space. And so if we have an air-filled porosity that's less than 20% of total pore space, and remember, ideally, half of our soil volume is pore space, so 10% of the soil volume, we'd inhibit plant growth. So here's a rule of thumb, a cutoff of total pore space air-filled less than 20%, or less than 10% of the soil volume, inhibit plant growth, hence poor aeration. So we have concentration of oxygen and CO2. We have air-filled porosity as two metrics, and we go on, there's more. And the next one is oxygen diffusion rate, abbreviated ODR, oxygen diffusion rate. And we measure this. We can measure the rate of movement of oxygen to a platinum electrode, which I'll show in the next slide. But here are the cutoffs. So note these numbers, around 0.3 to 0.2 microgram amount per unit surface centimeter squared per minute. This is the unit for a diffusion rate. Amount, microgram per area, centimeter squared per minute. Okay. So when we get this cutoff, 0.3 micrograms per centimeter squared per minute, when we get below that, top growth of plants generally stops. When we get below 0.2, root growth ceases. Okay? So this 0.2 to 0.3, this is an important cutoff. And here's another way for us to assess aeration. We can measure the oxygen diffusion rate. If we exceed these numbers, we have good aeration. If we are below this cutoff, we tend to have poor aeration. Okay, so we just added another metric onto gas concentration, onto porosity, air-filled porosity, and now oxygen diffusion rate. So this is our third metric to assess soil aeration. But there's more. Here's a picture of how that works, right? So this is done by a platinum surface, so we have this platinum surface in the soil, okay? And by the change in voltage, we look at this reaction, oxygen is reduced to water, and so this reaction, we can measure the rate of O2 delivery to this surface by this change in voltage, okay? It's by an electrode. It's pretty tricky, it's very sensitive, it's a pain in the neck, but we can measure the oxygen diffusion rate and get a reading of this in micrograms per centimeter squared per minute. We can get a reading and actually have a measure. So here's another way, this is our third way to assess soil aeration. Right? And here's a picture of how it's done. Yeah, it's tricky, it's a lot of work, and it's usually just done on a research basis. The ODR. Here's an illustration. So I had a colleague, a good friend at University of Georgia, and had a couple of grad students kind of look at the oxygen diffusion rate and how that impacted different systems. It's a greenhouse study. He was using cotton, and one of his other students was using sweet gum and biomass roots. And so here's a plot. So here's a plot of the percent success, okay, by the oxygen diffusion rate. And this is, and note this is grams, 10 to the minus 8th per centimeter squared per minute. So the micrograms is off by another 10 to the minus 3. But here's a number going along that measures the oxygen diffusion rate and some kind of success. So for loblolly pine seedling emergence, okay, when you start to get down to this, to about 5 or 6, okay, the rate of seedling emergence goes to 0. So there's a linear increase as the oxygen diffusion rate increases below that critical value, and pretty nicely goes all the way to 100%. Okay? So here's one example showing when you get to this threshold value, we essentially cut off biological activity or seedling success. So that's for trees. Right? So another one of his students looked at cotton root biomass and the percentage of cotton root biomass, and the same story, the same linear relationship, and not too far from the same intercept. Right? And so we have this change, and again, it's interesting that both these systems are parallel, the response is parallel. Here we have tree seedlings, and here we have cotton root biomass, but both ceasing when you get down toward those threshold values of those limiting oxygen diffusion rates. Okay? So again, just an example to illustrate that point, and I just happen to use it because one of my good friends and colleagues at University of Georgia had a couple of his students work some of this out when he was studying soil aeration. So pretty cool, right? And another way, there's still more. I've given you a bunch now. Let's go to the fourth. I have to tell you something so I can ask you on the exam. Right? So redox potential. And we abbreviate that, we illustrate that with a capital E and small h. So redox potential, the tendency of a system to oxidize or reduce. We measure it in volts or millivolts. Okay? It's a difference in voltage across the electrodes. So here's how it works. Oxygen accepts electrons, right? So in our aerated system, oxygen's there, it's accepting electrons, it's reduced to water. That's good. When oxygen disappears, it's no longer ready to do the job. So when there's no oxygen, no dissolved oxygen in the soil air, no oxygen at all, anaerobic, right? So anaerobic conditions, you get rid of the oxygen and something else has to take the electrons. There's still respiration, anaerobic respiration, stuff's happening, but it's slowed down considerably. So what are the other things that accept electrons? Things like iron and manganese, which we'll talk about. There are other successes, as you get more and more electronegative, there are other elements that accept electrons. If you use up the oxygen, something's got to take them. Where do they come from, these electrons? They come from respiration. Respiration, here's an example, it's just a word example. If you've taken organic or bio, you'll recognize this. If you haven't, I'll tell you about it. Glucose is the sugar, that's broken down and that releases energy. This is called respiration. So we release pyruvic acid, some hydrogen and some electrons. So the key here is I'm breaking down, organisms are breaking down glucose biologically, biochemically, and producing electrons, okay? This is respiration. Cool. Some of you are, I think, in this class actually sit in organic chemistry after this, so you'll be familiar with this, I think. Others, not so much. So let's kind of put some of these together in a picture, and this, I've taken apart a picture of the text from page 291 of figure 7.7. And I'm going to rebuild it, and so I'm going to rebuild it in pieces so that you can see what I'm talking about. So let's look at the concentration of these various elements, okay? And let's plot that over time. And time might be days, it might be weeks or months, depending on how much the system, where we are. Okay? But concentration versus time. So let's start with O2. So we have a rainstorm, we saturate the soil, and what happens? The concentration of O2 goes down, dissolved oxygen goes down. It gets used up until there's none left, okay? Unless we bring some air back into the system. So here it is, the concentration of O2, saturation is marching down, 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 gone. Nitrate is the next thing in line to get electrons. So as oxygen's depleted, nitrate is around, so nitrate starts accepting electrons. Okay? Nitrate's open for business. It gets reduced, and finally, after all the nitrate's gone, voila, that's used up, all that's reduced. So oxygen's first, nitrate's reducing the second. Electrons are going to oxygen when it's aerobic. Oxygen depletes, starts going to nitrate, the next electron acceptor. As we look at that, we could plot the EH, we could plot the redox potential, and we see it going down, down, down. Here's the number for EH, it's being reduced as the system becomes more anaerobic. Now, after nitrate, manganese is the next electron acceptor. So manganese is reduced. Manganese plus 4 goes to manganese plus 2. Okay? It's reduced, and it's picking up the electrons. And there we go. So you reduce manganese plus 4, you're increasing the reduced form. After manganese, iron, okay? Iron plus 3 goes to iron plus 2. So you see more iron plus 2 in the system, it's reduced iron. And when you use all of those up, manganese and iron, then it's sulfur. And so you're producing, you reduce sulfur, you produce hydrogen sulfide. So that's the next big piece to come in play, hydrogen sulfide. Now we're starting to get really anaerobic and stinky. And finally, carbon dioxide and other carbon compounds are reduced to methane. Those gas bubbles up, and this is a very, very anaerobic system. So carbon is the electron acceptor, methane is produced, and there we go. So we start out with oxygen, we get rid of that, nitrates accepting electrons, then manganese and iron are accepting electrons, then sulfur, and we're getting progressively lower and lower EH, more and more reduced. And there's the picture from 7.7, figure 7.7 on page 291. Meanwhile, the pH over here is changing, and so they've got a slot the pH actually rising in these systems. Okay. There it is, the pH going from here as you get more and more anaerobic starts to go up, more and more reduced. Kind of interesting. So there it is. I've taken it apart. Right? Now I put it back together in nice color form for you. And when I was a kid, we had color forms, but they were these little plastic things that you'd paste on a board and build little figures with, color forms. You probably never heard of color forms, but it just popped into my brain that was, when I was a little kid, we always wanted to get the color forms. So and ask your parents, maybe ask your grandparents, what can I say? But here it is, here's this rebuilt graph, right? As organic carbon is donating electrons, and then all these things, oxygen's going down, it's reduced to water, nitrates taking the next bunch of electrons, then the sulfates and manganese, all these things happening progressively and progressively, more and more negative, lower EH, right, getting more and more negative, and voila, at the end, we're into very anaerobic conditions. And here's the picture of that all in one graph. Pretty cool, right? So this graph, like all the graphs we've talked about, packs in a lot. It packs in all those concepts and expresses them. So as you study, one thing to remember, if you can take apart this graph and put it back together, it'll be very helpful. It's a useful one to kind of put on an index card and think about. Aerobic up here, right? We start removing dissolved oxygen. We get to anaerobic and anoxic down here at the very bottom, and then poor aeration, suboxic. So here's a picture of these three terms: aerobic, poor aeration, suboxic, and anoxic, very anaerobic. EH decreasing precipitously, getting smaller and smaller. So those things are all happening at the same time. So, and I think I mentioned 4 or 5 ways to assess aeration. They're all related, right? So here's a graph from a bog peat system that shows EH, okay, EH measured in millivolts. EH is the redox potential versus oxygen diffusion rate. And again, micrograms per centimeter squared per minute. And you look at this, and they're pretty positively related, right? As the oxygen diffusion rate increases, the EH increases. Okay? And EH goes from negative to positive. So very low EH, very high EH. And so this illustrates that these measurements are correlated or related. Okay? Here is the shape is nonlinear, but they're two correlated. If you have EH, you have a pretty good indicator of ODR and so forth. So what's going on with iron? Okay, so I talked about oxidation reduction. So let me show you a little picture of the molecular viewpoint of what's going on. So here I have FeO, it's +2. So what happens when I oxidize that? I increase valence state, right? So I go from FeO to FeOH, okay? I consume electrons, right? This shows I go from +2 to +3. This shows the oxidation of iron as the change in valence, okay? It's consuming electrons. Iron is oxidized, but where do those darn electrons go, okay? So in this case, oxygen, right? There's oxygen in the system. Oxygen takes the electrons and is reduced to water. And this is an aerobic system. Iron is oxidized. Oxygen takes the electrons. Oxygen itself is reduced. So something's oxidized, something's reduced. again, aerobic systems, oxygen's there, oxygen gets the electrons, they don't go to iron, and then oxygen grabs these electrons, is reduced to water. It's an aerobic system. Pretty neat. We put all that together, right, and we show the change in valence. We show the consumption of electrons. We add that to the reduction of oxygen, and it just boils down to this equation. Iron oxide in the presence of oxygen goes to FeOOH. And this is the bottom line. This shows the consumption of electrons, the reduction of water, and then adding that all together. Again, aerobic system, presence of oxygen, oxygen getting the electrons, iron, everything else can stay oxidized. Oxygen doing its job. So as we deplete oxygen, other things get the electrons, and hence we go back to that chart we showed, just that figure in the text with the multicolored figure that I took apart. This is the summary of that. So there's another way, yet another way, to evaluate the capacity of these soils to be well aerated, and this is relatively new, the last 10 years, something called IRIS. So this is a neat idea. It was some of my colleagues kind of figured this out. And IRIS stands for Indicator of Reduction in Soils. Indicator of Reduction in Soils, IRIS. And so we have these tubes we paint with iron oxide. So here's a picture. So these are some tubes out in Montezuma. We put these in a wetland to see how well they worked. And so you have these tubes, right? They're essentially PVC tubes, and you paint them with an iron oxide paint. And here you can see. So what happens when reduction occurs? When reduction occurs, iron gets the electrons and is reduced. Reduced iron is soluble. So when you reduce the iron coatings you have on these posts, on these PVC tubes, it dissolves away. And so hence you can see visually the result of reduction. The iron is reduced and it gets off, the coating is removed. And see all these light areas. This is all be done in anaerobic areas where oxygen is limiting and depleted. Iron gets the electrons, and voila, you can visually see that. Now we can also do this. We can do some image analysis on this and get the relative percent as an index. Right? So, but this is the mechanism, the reduction of iron, allowing this paint to dissolve, reduced iron, and it dissolves and floats off and becomes no longer associated with the PVC tube. Iron, these amazing. So this is pretty cool, right? This is a neat technique. It's visual, and you can get a quantitative measurement by the proportion of the paint that's been removed. So this was done. So I showed you that one site. This is a shot of the site out at Montezuma Refuge. And so these were installed, and it pretty well demonstrates that they effectively show anaerobic areas. Now there's another way to do this in manganese. So manganese also, it turns out, is changed by a reduction. Okay? And so you can do the same thing. If you can paint a coating of manganese and then reduce it to manganese +2 from manganese +4, it does the same thing. It dissipates. So here's a picture of a bunch of tubes called MIRIS, the manganese indicator of reduction in soils. Right? Pretty neat. Different than the iron reduction, but the same idea. The interesting thing about this is that when you have high pH soils, the IRIS tubes don't work that well. Under high pH, some of that reaction is controlled by something called siderite. It's an iron carbonate. So when you get high pH soils, instead of using the IRIS tubes, you use the MIRIS tubes, okay? Manganese. So they both work, and so it allows us to adjust for pH. But again, both of these, a visual illustration of the impacts of reduction on systems because the paint goes away. So that's pretty unique. And I still remember when this came out in maybe 10 or 12 years ago in the Soil Horizons. This was a new idea. So this, to me, it was pretty rocking, right? And comparing both of those, okay, on a well-drained site, very little, and then on a poorly drained site, high removal. So it, again, illustrated that these things work pretty well. So let's go back to the EH of a well-drained soil. Okay. And so one of the ways to qualify that. So let's look at what oxidized form of oxygen and the reduced form, and let's look at the change in EH. This is the reduction potential, redox potential, and it's measured in volts. So as oxygen is reduced to water, the EH is in the range of 0.38 to 0.32. It's just a measure. Remember, we just put this probe in, we measure the EH, and we get a value, difference in voltage. When all the oxygen is depleted, nitrate becomes the electron acceptor. Okay? So nitrate is reduced to N2. The range of EH that this occurs is 0.28 to 0.22. Okay? So we're getting smaller. The system is becoming more towards anaerobic. After all the nitrate is used up, manganese is next, and manganese is reduced from Mn+4 to Mn+2. Note the change in valence, reduction in valence. And this occurs in the EH in the range of 0.22 to 0.18. So we're getting smaller yet. We're getting less and less oxygen, more towards anaerobic and anoxic. Once the manganese is used up, the next electron acceptor is iron. Iron goes from +3 to +2. It's reduced. And the EH range is 0.11 to 0.08. Again, we're getting lower and lower EH. Sulfate, the next one down the list, as iron is used up, sulfate starts getting the electrons, and sulfate is reduced to hydrogen sulfide, that stinky gas, right? So now we're getting into really anaerobic systems. And now we're down to negative values for this redox potential, minus 0.14 to minus 0.17. And then we finally get down to carbon dioxide being reduced to methane, bubbling up and getting the gas. This is extremely low EH, anoxic, minus 0.2 to minus 0.28. And so we're getting successively smaller and smaller EHs as we deplete oxygen, and other elements, other compounds take up the electrons, become the electron acceptor. Okay? So there's the series, and now this kind of corresponds to our graph. We have that graph that showed the same kind of sequence, oxygen depleted, then nitrate, then manganese, and here it is in a table. Okay? And so we have it both in a tabular form, and I've presented it as well as a graph. And these things kind of come together. Now from these graphs and from these table, I can ask you the question, what is the EH? What value should we associate with a well-drained soil? And a well-drained soil, well aerated. And if looking down this, what might you expect, right? Here we're starting to see just the loss of oxygen. Here we're seeing loss of nitrate, and all these things are reduced. So if I look at this and I think, where above this is oxygen plentiful before it's reduced to water, okay? And it's in the range of 0.4 to 0.7. So here's our metric, here's our cutoff for a well-drained, well-aerated soil, an EH value of 0.4 to 0.7. So we're adding this to our metrics, we're adding this to our concentration of CO2 and O2, we're adding this to the air-fill porosity and total porosity, and we're adding this to the ODR. This is our fourth metric of a way to assess aeration, a well-aerated soil. Okay? All of these are related, okay? But these cutoffs are important. So you should know that the cutoff, a well-aerated soil is generally in the range of 0.4 to 0.7 volts, or 400 to 700 millivolts. Okay? So know these thresholds. So now we've quantified it, right? We've described it and defined it and shown the march of different molecules. And now we think, let's kind of take a step back and let's consider the factors affecting soil aeration. Right? Let's bring it back to physical properties. And first we have to say macro pore space. Right? Macro pore space. texture, what affects macropore space. So we go back to our physical properties lab, and macropore space is essentially driven by texture, aggregate stability, bulk density, and organic matter. So those are the big factors. And we've talked about each one of those individually. We've talked about finer textured soils and relationship to pore space and aggregate stability. We've talked about bulk density and total pore space. And we've talked about organic matter and how it influences structure and how it influences bulk density. And so we go back, so now we're building on the material, the information that we obtained when we did the soil physical properties lab, and now we're applying this to think about aeration. And we also have, with this, we also have an indicator threshold values of measuring the aeration. Okay, so we're tying these together in this lecture. The other thing is depth in the profile. And so depth in the profile, as you imagine, we talked about the exchange of energy, water, and gases being maximum at the surface and decreasing with depth. And so it is, it ties together with macropore space and diffusion. Okay. So next thing is biochemical reaction rates. The microbial decomposition of organic residues. This consumes oxygen and generates carbon dioxide. Roots and higher organism activity also involved in respiration and production of carbon dioxide. So these biochemical reaction rates of microbial decomposition of organic residues and the activities of roots and higher organisms, these affect soil aeration. If you produce more CO2, you've got to get rid of it. If you consume O2, you need more of it. So these reaction rates are driven by that. Season. There's a seasonal march to this. So let's look at this is a really cool graph. It doesn't appear in the 15th edition, but I use it because it's so illustrative of the interaction of depth and season. Okay? This shows the concentration of soil carbon dioxide by depth seasonally going from June to November in a cornfield. I want to say a corn plantation, a cornfield. And so we start June, and we see the concentrations are relatively low and they increase with depth. So we expect concentrations of carbon dioxide to increase with depth. And 0.3 to 0.5% carbon dioxide, 0.5 to 1%, we're getting well above atmospheric, and then 1 to 2%. And as we get into mid-June, when the root activity starts heating up, there's an interaction, there's a bump in the CO2 in the maximum biological activity in the root zone. So it's it's increasing, but then it has this big bump here and then goes down again. So here's this interaction with depth affected by biochemical reaction rates. As we get into August and the root growth is starting to slow down, the corn slows down, those numbers dissipate again, okay? And as we get into September and the end of the growing season, they dissipate yet again and then go back to lower levels. So here's a seasonal interaction between depth and carbon dioxide based on root activity. Well, 7% concentration, greater than 7%. That's pretty high. It's starting to get close to the 10%. It's still not toxic, but it's pretty high. And so we see this magnificent interaction with depth in the season here in the height of the growth of roots, and these corn are just growing like mad, cranking out carbon dioxide, root respiration. And that begins to dissipate. So the question to keep in mind, 7%, what is that relative to atmospheric concentration? So I'll ask you that. We'll pick that up next week when I return from my trip. I'll be returning on Friday. I'll be grading exams all weekend, and then I'll see you again on Monday. We'll meet again, and we'll pick this up. We'll wrap up soil aeration with this question, and then we'll begin with soil temperature. And with that, wish you a great weekend. Now that the test is over, or the test will be over Wednesday, their weekend should lighten up a little bit, and you can work on other stuff. So I'll see you next Monday.